Okay, so I kind of made that hard on you on purpose by moving it around and distracting you and confusing you. But even if it's not moving at all, it's a little bit, tricky to do. You probably stare at it a couple of times. Your brain is going back and forth and back and forth. And so text analysis is one of the great things that computers are very, very good at. And some of the things that, they can translate text, and that's because they've looked at a lot of information. So looking at text is actually something computers are really good at. And so if we take a look at the kind of programs that we're going to write to do this kind of thing, this is something that humans are not naturally good at, but computers are super good at. Now, I'm not going to have you look at this code. This code you will understand in a few weeks, but basically this is a set of instructions to open a file, read that file, read all the words in the file, create a histogram of all the words in the file, and then search through that histogram to find the most common word and tell us what the most common word is in the file. And in this clown file, the word "the" is the most common. It happens 7 times. And here's another large file called words.txt, and the word "to" is the most common thing. And our goal is to get to the point where you can write this on your own. So you can say, you know what, I got a problem to solve. That is, what's the most common word in this file? I know how to start, and then I know how to finish. I know how to do the stuff in the middle. And we have to learn this kind of weird language, but when we do, we can count millions of words as easily as you count 20 words. So that's the fun of all of this, is to teach you this language so that you can solve that problem so that you don't have to solve it. Because you could solve it, but it's not something you're naturally good at, and it's hard work. So up next, we're going to talk a little bit about the hardware architecture that you're going to be experiencing as you write programs. Hello and welcome back to Hardware Architecture. Now you might ask, why do I tell you about hardware architecture? Probably you're not going to build any hardware, although it's fun stuff to do, and if you're going to become a computer scientist, which most of you won't want to be, it's a great thing to study, and those who build our hardware are amazingly talented individuals, and it's a really rewarding job. The reason I like talking to you about hardware is because I want to be able to use words at some point and say, oh, secondary storage, or central processing unit, or random access memory, or peripherals, input devices. And I want to be able to say those words, and I want you to be able to understand them. And so I'll start with a little piece of hardware called the Raspberry Pi. And the Raspberry Pi is a cute little single board computer. As we go forward, these things are smaller and smaller and smaller. And the interesting thing is that the architecture of these stays the same, but the number of components drops. So I'm going to start and give you a block diagram of sort of a generic computer and tell you the major parts of it. Now, I'm going to show you some really old hardware, some really new hardware, and then some hardware that is of medium age. And the medium age hardware is probably the easiest one to see. The architecture is the same, okay? And so the basic block diagram is that the brains, if there are brains in computers, which there really aren't, the software is the closest thing computers have to brains, but in hardware, the closest brain a computer has is this, called a microprocessing unit or a central processor unit. And this is designed 3 billion times a second to ask the question, what do you want me to do next? And these little pins on the back are our instructions, like 32 or 64 of these pins. 3 billion times a second, we send an instruction into these things. Now, we can't sit there and talk to it. We can't. And so the instructions we store in what's called the main memory. And this memory is really fast. And the memory sort of feeds this. And so every time the CPU needs a new instruction, it asks the memory where that instruction is. And so the memory feeds the instruction to the CPU does it, says give me another instruction, CPU does it, gives me another instruction, and that is the basic essence of programming. This asks what's next, and this is where your program is stored, or a program you purchased or came with your hardware, where that's all stored. And those are your places. And so you end up inside, your programs end up inside this memory. So then there's a, I mean, and so in software you tend to program the CPU, and if you had bought a desktop computer a number of years back, it would have this thing called the motherboard. And the motherboard is called this because it kind of connects all the components together. And so if you buy memory by itself, it does nothing, but it has a place to plug into the motherboard. And if you buy a microprocessor, it has a place to plug into the motherboard. And if you buy a hard drive, this is a really old hard drive, it has a place to plug in on the motherboard. And so the motherboard sort of connects everything together. The hard drive is secondary storage. Now, the way how secondary storage is different than the main memory, which, there it is. I got unpile this stuff. So this main memory is really fast, but as soon as you turn the power off of this memory, it sort of vanishes. And so to store files like word processing files or text files or whatever, you got to store it on something that lasts a little bit longer. And so that's the purpose of the secondary storage. It's permanent. When the power's off, it stores it. Now this one here is in such bad shape that isn't probably storing anything, but it's got these little heads and it spins around and goes in and out. And we'll have a video later that shows you one of these things that's not quite in as bad a shape. If you look, this has 4 different platters that are all spinning around. And so this is just using magnetic material and electronics that sort of magnetize and demagnetize this stuff. And if you look at a disk, they're often rated, physical disks are rated in revolutions per minute, and that's how many times this thing spins around. And if you got an old desktop and you hear it spin up, this is the thing that's spinning. And it's the place that your operating system lives, your files live, your applications live, while they're stored and while the computer's turned off. And then they're loaded into this while they're running, and then this CPU takes the data from the main memory, and your program runs at 3 billion operations per second. So, let's talk a little bit about something that this is probably from the 1960s or 70s. This actually has, if you're an electrical person, it has capacitors. Those little silver things are capacitors. These little colored things are resistors, and that's more capacitors. And then there's wires, and wires move everything. And so when you say like this has millions of transistors, oh wait, that isn't a capacitor, that's a transistor. That's a transistor. When you say that this here has etched, and if you look closely at this, go look at a picture of a microprocessor online, you will see that it has millions of these. And so the difference between 1960 and today is this circuitry of capacitors, resistors, and transistors has been microized and put onto this. It's using a photographic process, and they're tinier and tinier and putting more and more on. And if you think going from millions of these to one of these is crazy, the thing that's happening now, and the reason we have whole computers inside our pocket, is that everything, all of this whole thing, CPU, memory, everything, all of it connected, and the storage is being made smaller and smaller. And so this little single board computer called a Raspberry Pi has one thing in it, and it has the main memory, and it has the CPU, it has connections for things like peripherals like keyboards and stuff. Now it doesn't yet have secondary storage on it. The secondary storage gets plugged in right here via USB. And then if you take it one step farther to my phone, it's got the secondary storage built right in. And so, you know, this picture goes from the size of cabinets in the old days all the way down to really tiny. But at the end of the day, inside it is a highly sophisticated piece of circuitry that asks for instructions one at a time, and main memory that holds the instructions and feeds them. Okay? Central processor does the thinking. Let's take a look here. Central processor does the thinking. It runs the program. It's asking what's next. It's not really smart, but it's really fast. And so we